Section 5.2, the characteristic equation. In the last section, we asked the question, how do we find eigenvalues of a matrix? And if you remember, we said that we would find out in the next section. So here's the section where we're going to find that out. So first, let's look at an example. We want to find the eigenvalues of this matrix A that we're given here, and it's a 2 by 2. So what we want to do is we want to find all the scalars lambda such that our equation a minus lambda I times x equals 0 has a non-trivial solution. So what we mean is we want a minus lambda I to not be invertible. Because remember, if that matrix is invertible, then our homogeneous equation there has to have only the trivial solution. So first, let's find what a minus lambda I is. So we have our matrix A first, and we're going to subtract then lambda multiplied by the identity. So that means we're going to have lambda on the diagonals with 0 everywhere else. And so we then end up with this matrix here, 0 minus lambda, 1, negative 6, and then 5 minus lambda. So we're looking at this, which ends up being then negative lambda, 1, negative 6, and 5 minus lambda. And remember, we're wanting to find out when this matrix is not invertible. So it's a 2 by 2 matrix, and it fails to be invertible when its determinant is 0. So we want to find when will it happen that the determinant will be 0. So the eigenvalues of A are then the solutions of our equation, the determinant of a minus lambda I equal 0. And this equation is called the characteristic equation. So in our case, we have a minus lambda I is equal to negative lambda, 1, negative 6, and 5 minus lambda. So we want to continue that example here. So then if I take the determinant of a minus lambda I, then I will multiply by diagonals, so I'll have negative lambda times 5 minus lambda minus negative 6 times 1. So if I multiply here, then I'll get negative 5 lambda plus lambda squared minus a negative 6, which becomes plus 6. And I'm going to reorder this, so I'll have lambda squared minus 5 lambda plus 6. And we're going to pull from our algebra base here and factor this. So we know that it factors as lambda minus 2 and lambda minus 3. And remember that our characteristic equation, we're solving when the determinant is equal to 0. So to solve this, we set both equal to 0, and we end up with eigenvalues of lambda equal 2 and lambda equal 3. So the determinant of a minus lambda I is called the characteristic polynomial. And you see how we ended up with a polynomial here. To make this meaningful in general, we would need to define the determinant of any n by n matrix. So a scalar lambda is an eigenvalue of an n by n matrix A if and only if lambda satisfies the characteristic equation when we take the determinant of a minus lambda I and it is equal to 0. So let's look at another example. We want to find the eigenvalues of this matrix A, which is a 3 by 3 matrix. So first we're going to find what a minus lambda I is. And so we're going to subtract from this matrix our lambda multiplied by the identity, which means we're going to have zeros everywhere else and lambda on the diagonals, like this. And we'll end up with this matrix here, and we're looking at our diagonals where we have lambda. So we want to find the determinant of A minus lambda I. So this middle row has some zeros on it, so that's going to be the easiest one to look at. And so we will pull out our middle coefficient. So we're going to be multiplying -5 minus lambda. We're going to eliminate that row and that column. So then we're left with a matrix that is 1 minus lambda, 1, 1, and 1 minus lambda. And remember, if we did our matrix of signs, we have plus, minus, plus, minus, plus, minus. So our middle term is going to be positive. And now when we take the determinant of this, we're going to still have -5 minus lambda. And then I'm going to multiply that by the determinant of this 2 by 2. So I'm going to multiply 1 minus lambda times itself, 1 minus lambda, minus then 1 times 1. So we have -5 minus lambda now multiplied by 1 minus lambda squared minus 1. So I'm going to FOIL that out. I have -5 minus lambda multiplied by 1 minus 2 lambda plus lambda squared and then minus 1. So the 1's cancel. And I end up with -5 minus lambda times -2 lambda plus lambda squared. And now we're going to FOIL that out, and we will end up with 10 lambda minus 5 lambda squared plus 2 lambda squared minus lambda to the third. So then now when I combine like terms here in the middle, and I'm going to reorder it, I'll have negative lambda to the third minus 3 lambda squared plus 10 lambda, which I can now factor out negative lambda, and I'll have lambda squared plus 3 lambda minus 10, and that factors then as lambda minus 2 times lambda plus 5. And we want to set that equation equal to 0. So I'll set all 3 of my pieces equal to 0, and I'll end up with lambda being equal to 0, 2, and -5. So those would be the eigenvalues that we came up with. So remember how we added on to our invertible matrix theorem in the last section? We're going to kind of add on again. The invertible matrix theorem, we added on S, remember, from the last section, and said that the number 0 is not an eigenvalue of A. If it is, then A is not invertible. So then we can now also add something talking about the determinant, and we know then that the determinant of A cannot be equal to 0 if our matrix is invertible. So now let's look at Theorem 3. We're going to let A and B be n by n matrices. We know that A is invertible if and only if the determinant of A is not equal to 0. The determinant of A times B is the determinant of A times the determinant of B. The determinant of A transpose is equal to the determinant of A. If A is triangular, then the determinant of A is the product of the diagonal entries. And then row replacement doesn't change the determinant at all. Row interchange will change our sign, and then scaling will scale the determinant by the same factor. So this is just a review of what we looked at in Chapter 3. So for example, if we let A be this matrix here, then the determinant of A is going to be 4 minus 6, which is negative 2. Since we know that row replacement does not change our determinant, then if I multiply the first row of A by negative 3 and add it to the last row, I'll produce this matrix B here. So then the determinant of B is negative 2 minus 0, which is negative 2, or the determinant of A. So that did not change our determinant. Now we're looking at row interchange. If I change the rows of A and produce this matrix B here, then the determinant of B is going to be 6 minus 4, which is positive 2. And that is the negative times the determinant of A. And now we're going to look at scaling. If I multiply the first row of our matrix by 2, we get this matrix B here. So then the determinant of B would be equal to 8 minus 12, which is negative 4. And that is 2 times the determinant of A. So this was just a quick review of what we learned about determinants in Chapter 3. So now let's look at an example. We want to find the eigenvalues of this matrix A given here. So remember that to find the eigenvalues, we were going to set the determinant of my equation A minus lambda I equal to 0, and we want to solve for it. So A minus lambda I is going to be equal to this matrix here. So since this is a triangular matrix, the determinant is just going to be the diagonals multiplied together. So our characteristic equation is going to be 3 minus lambda times 6 minus lambda, then times 2 minus lambda. And we're going to set that equal to 0. So it's already in a factored form, so I don't need to multiply it out, but I set each factor equal to 0, and I'll get the eigenvalues lambda equal to 3, 6, and 2. Something to take note of, the algebraic multiplicity of an eigenvalue is its multiplicity as a root of the characteristic equation. So we're going to look at this example here, and hopefully you're noticing that we have 3 repeating itself in the diagonal. So we're going to have a multiplicity here. This root will be a multiple root. So what we're going to do then is find first A minus lambda I, and that'll be this matrix here. So when I find the determinant of A minus lambda I, then I'm simply going to use the diagonal entries because I've got all zeros, and I can just multiply those. So I have 2 minus lambda times 3 minus lambda times 3 minus lambda again, and then times negative 1 minus lambda. And I want to set that equal to 0. So what we have then is our eigenvalues. Lambda is equal to 2, 3, and negative 1, and 3 has a multiplicity of 2. So you could also have listed it out if you wanted and said 2, 3, 3, negative 1 to demonstrate that there's a multiple root. So now let's look at a definition. If A and B are n by n matrices, then A is what we call similar to B if there exists an invertible matrix P such that when I multiply B on the left by P and on the right by P inverse, that is equal to A. Or similarly, that B is equal to P inverse times A times P. So that being said, let's look at theorem 4. If A and B are similar, so they have that matrix P such that that relationship holds, then they have the same characteristic polynomial, and hence the same eigenvalues with the same multiplicities. So we're going to look at a proof if B is equal to P inverse A times P. And that's assuming that A and B are similar. Then, if I subtract lambda I from B, that is equal to P inverse A P minus lambda I. But we're going to replace lambda I with simply lambda times P inverse P, since this is equivalent to the identity. So now I'm going to move my scalar over, so I'll have P inverse A times P minus P inverse times lambda times P. I can do that since it's a scalar. But now that allows me to pull out P inverse on the left and simply multiply it by AP minus lambda P. And that's equal to P inverse times AP minus lambda I times P. So now I can pull out P on the right, and I have P inverse times A minus lambda I multiplied then by P on the right. So then the determinant of B minus lambda I is equal to the determinant of P inverse times A minus lambda I times P. And using our rules of determinants, that's simply equal to the determinant of P inverse times the determinant of A minus lambda I, then times the determinant of P. But remember that the determinant is just a scalar, just a number. So we can move that around, and so I will then have, I can move the determinant of P inverse over to the middle, so that will be equal to the determinant of A minus lambda I times the determinant of P inverse P. And so basically I've moved it over and then gone backwards in my definition. But we know that P inverse P is simply I. So the determinant of I is 1. So what I have then is that the determinant of B minus lambda I is equal to the determinant of A minus lambda I. So this means then that A and B have the same characteristic polynomial and the same eigenvalues.